let's have a bit more of a look at complex numbers on the Argand diagram, so the pictures that they create. And we briefly mentioned circles the other day. Let's just have a look at these in a little bit more detail. So there's our basic circle. Now, before I said, oh, we could write this as z times z conjugate is equal to r squared. We've got a much neater way of doing that now, because since then we've learnt something called modulus. And so a much more logical way to think about it is that all the points on that circle have the same modulus. They're all the same distance from the centre. So a much neater way of writing this would be simply that the modulus of z is equal to r. We see that. We see mod of something is equal to a constant number. We know we're talking about a circle, because we're saying all the points are the same distance from another point. So if the circle is not at the origin, but some other complex number, yeah, we saw that if we write it in conjugate form, it looks something like this: z minus omega times conjugate of z minus conjugate omega is equal to r squared. But again, a much neater way of thinking about it is that if I was to draw a vector from all those points on the circle and join it up to omega, every one of those vectors would have the same length. And so that's what that basically is saying. The length of the vector z minus omega is always the same. We get a circle. So basically, modulus equals a constant. We got a circle. So let's have a look at these circles. Start with a very easy one. X squared plus y squared is equal to 16. We know that's a circle, centre at the origin. Radius is 4, so it would simply be the modulus of z is equal to 4. If you did want to put it in conjugate form, it would be z conjugate is 16. This one we'll need to complete the square on to come up with the equation. So half the coefficient, I've moved the constant over first of all. Then half the coefficient of x is 3, so I'll have x plus 3 squared. Half the coefficient of y is negative 2, so we have y minus 2 all squared. That creates some more constants, so tidying that up, 3 squared's 9, 2 squared's 4, 9 and 4 is 13. If I've added 13 to the left side, I've got to add 13 to the right side. Thus we get 25, but in that form, we know exactly what our circle is. Centre minus 3, 2, radius 5. So as a vector, what we're saying is, if I was to join our random point that's moving on this, what we know to be a circle, if I was to join it to the complex number negative 3 plus 2i, because remember, just like in coordinate geometry, it's z minus the centre. So the actual centre is not 3 minus 2i. The centre is minus 3 plus 2i. But if I was to join that up, its length would be 5 for all these. In conjugate form, I think it looks ugly, these sort of ones, but there it is. Z plus 3 minus 2i, conjugate of z plus 3 plus 2i is 25. All right, let's go back the other way. Let's find the centre and the radius. So here it is, modulus of z minus 5 minus I is equal to 2. So the way to think about it is, well, if I join z up to the complex number 5 plus I, its length will always be 2. Thus, I have a circle with centre 5, 1 and radius 2. Well, let's look at one in conjugate form, because sometimes we might get asked in that format, so we do need to interpret it. We've got z plus 4 plus I, conjugate of z plus 4 minus I. So it is in the form that we have recognised to be a circle. The centre, remember, we look at the first one, and again it's z minus the centre. So the centre is not 4 plus I, but the centre would be minus 4 minus I. So the centre is minus 4 minus 1, and in this format it is radius squared, not just radius. So the radius is 7. Remember, if ever you're unsure with any of these, you can always replace the z with x plus iy, and then just go back to coordinate geometry, and hopefully you'll recognise the Cartesian equation of what you come up with. This one's not immediately obvious. The modulus of 3z is equal to the modulus of z. So we're saying the length of the vector that joins z up to 2, no, it'll be minus 2 plus I, is going to end up being 3 times the length of the vector when we join it up to the origin. What on earth is it? Well, let's make it a little bit easier. We can factorise the 3 out, so I've done that. So 3 times mod z still doesn't look that familiar. So I'll chuck it into x plus iy form, and hopefully I'll recognise what we get. So modulus of z is x squared plus y squared, or the square root of. So that's why this has become 9, because I've squared both sides as well to get rid of that square root sign. On the right-hand side, it would have been the square root of, but again, we've squared both sides, so the square root's gone. The real part squared would be x plus 2, and the imaginary part squared is y minus 1. Let's expand it all out. It looks like we have indeed got a circle, because I'm going to end up with x squareds and y squareds. The coefficient's going to be the same. Let's move it all round to make it look like something we recognise. I like the coefficient of x squared and y squared to be 1 when I'm completing the square. So let's divide everything by 8. Okay, well, half the coefficient of x now will be minus 1/4. Half the coefficient of y will be positive 1/8. But now I've created new constants. Will be 1/16 and 1/64, which is how many 64ths? 1/16 is, how many 16ths and 64? 4? 4. So for 5/64ths, we're adding to 5/8ths, so we get 45/64ths. Messy numbers, but they are what they are. But at least now we can tell what the centre is and what the radius is. So centre 1/4 minus 1/8. Radius would be 3 root 5 over 8. Okay. So if ever you're unsure, doesn't look familiar, go back to x plus iy, have a look at what the Cartesian equation is, and then hopefully you'll recognise the shape. All right, z times z conjugate, we know that to be x squared plus y squared. Z plus z conjugate, well, we know that whenever we add a number with its conjugate, we end up with 2 times the real part. So I've got x squared plus y squared plus 4x. Again, another circle. Kind of not surprising seeing the heading of this bit was circles, I suppose. So we get x plus 2 all squared plus y squared is equal to 4. I recognise what that is. Centre minus 2, 0, radius 2. That's a bit of talk about lines. We talked about vertical lines and horizontal lines. So just as a reminder, remember the horizontal line, every point on there has the same imaginary part. So we can call that the imaginary part of z is equal to a constant. And on a vertical line, they all have the same real part. So we can call that the real part of z is equal to some constant. But of course, not all lines are horizontal or vertical. I've got one at an angle. Well, how do I create this line? I do it by thinking of a question backwards. And the question backwards is, find the perpendicular bisector of 2 points. I can always do that. So if I've got a line, it must be the perpendicular bisector of some 2 points. And so that's the idea behind this, that, okay, well, this line, I can always find 2 points that'll be the perpendicular bisector of. So if I see something like this, if it is the perpendicular bisector, it means the distance to one of the complex numbers is equal to the distance to the other complex number. And so the 2 vectors must be equal in length. Okay, now that I know that idea, anytime I now see this, where I see modulus is equal to modulus, I know I'm talking about a straight line, because that represents the perpendicular bisector of 2 points. So let's put it into context then. Here's one. Z minus 1 minus I, so we're saying the distance from Z to the point 1, 1, who was a racehorse, but that's another story, is equal to the distance of a point to -2, -1. Okay, again, don't recognise it. I could always go back to coordinate geometry. So I'm saying these distances or moduli are equal. If I expand out, sure enough, the x squareds and the y squareds cancel, and I end up with a straight line when I bring everything together. You could do it that way. It's not that much working out, I suppose. I mean, it does work. The other way I could do it is, okay, if I remember, it's the perpendicular bisector of these 2 points, 1, 1, and minus 2, minus 1. I just change the problem to be, find the perpendicular bisector of these 2 points. So I'll need the midpoint, because I know it'll go through that. I'll need to find the slope between the 2 lines, because if it's perpendicular, the required slope I need will be the negative inverse of that. I have a point, I have a slope, I can find the equation of a line. So y minus y1, etc. And sure enough, it comes out to be the same equation. So whichever method you prefer, really. I mean, the first one's not that long. But the second one can be useful when you get a question like this. It doesn't actually say find it, it just says sketch it. So if you know it's the perpendicular bisector, it's very quick to draw. Because, all right, let's have a look at this. We're saying it's going to be equal to the point, it's 2i, so that's on the imaginary axis, negative 2, and positive 4 on the real axis. So let's plot those. But for negative 2, that's a vertical line. So the perpendicular bisector must be horizontal. And it must go through the point, halfway in between minus 2 and 4. 1. There it is. And all I said was sketch it. I've done it. But of course, seeing it's horizontal, it would be very easy to come up with the equation anyway, if they wanted me to. Okay, I'm going to talk now about rays. You might not have heard this terminology since maybe year 7. You know, we have lines, we have intervals, we have rays. What is a ray? Yes, it was a long time ago, wasn't it? Remember? Oh, yeah. Yeah, that's a good way of saying it. Right? Remember, a line technically has no start and no end. It goes on forever in either direction. An interval has a definite starting point and a definite finishing point. So a lot of times on what we call lines, when we say, find the line AB, we're actually talking about an interval. Or the length of the line AB, we talk about an interval. A ray, definite starting point, but no definite finishing point. It just keeps going. So it's sort of like the mixture of the two. All right, let's draw one. There's a ray. Its definite starting point is at the origin, and it's going off at some angle I've called theta. Every point on that red line has something in common. What is it? Yeah. The angle it makes is always going to be theta, so its argument is always going to be equal. So if we see the argument of z is equal to some angle, we know we're talking about a ray. Notice I've circled the starting point though, because you can't find the argument of a single point. How do you know which direction you're going in until you actually start? So with a ray, we always circle the starting point. Of course, we can move our ray, and that's fine, because now all we're saying is the argument of the vector z minus omega. Because, all right, we know it starts, or the tail is omega, the head will be somewhere on that line. And so the vector would be z minus omega, and we're saying that argument is theta. So if it's not at the centre, and then if you think about it, that is what we've written here, because it's actually z minus 0, but we just don't write the minus 0. So let's see, we have to draw this. All the points such that the modulus of z is less than 1, and the argument of z is in between 0 and pi and 4. So now it's like regions in the plane. Mod z less than 1. We know we're talking about a circle. There it is. It's dotted because the boundary is not included. Are we inside the circle or outside the circle? Yeah, Because we're saying all the points such that its distance to the origin is less than 1, got to be inside the circle. Now, our rays, well, one of them starts, well, they both start at 0. One's going off at pi on 4, so I mark in the angle pi on 4. One goes out horizontally. They don't know about the handle. It's a bit tricky. It goes out at 0, and we're in between those. So the section we're talking about is just that little piece in there, that quadrant. Notice I've circled the boundary, because remember, regions in the plane, in dotted line, circle. All right, there we go. A few different exercises to look at.